Now, first of all, when it comes to scale up, you want to ask, why bother scaling it up? Is this just a case of making something bigger for no particular reason, rather like you making a bigger car for no particular reason? Well, I hope to show you that that's not the case with CCC. There are plenty of really excellent reasons why you might be interested in scaling up CCC. Here are some of them. Laboratory scale centrifuges can separate large quantities of material from a few milligrams to up to 10 grams or more. So you can separate out large quantities with only a small machine. You do not need a pilot plant, you do not need a manufacturing plant in order to get preparative quantities of material, as you do with other forms of chromatography. You use significantly less solvent than with Prep HPLC, so it's more economical. You get a very high sample loading. From 70 to 90% of your column is the stationary phase. And that's a very large percentage compared to HPLC, and that is the reason why you can do large quantities on a small machine. It can cope with crude extracts and particulates. Now that's an advantage even on a small scale, but on a large scale it is an even bigger advantage because you don't have to go through a complex filtering process. If you have a kilo of material and you're trying to filter, you could lose a lot of material. It can be very, very difficult. It can be expensive to filter. You can choose how to operate it. Now this is a great strength when it comes to preparative. You can use it in reverse phase mode or normal phase mode, or switch between the two. It is predictable and it's reproducible. That means that each time you come to a CCC machine and do your preparative run, you're effectively making a fresh column, which means your peaks will always come out at the same time. You're not getting any of this drifting of peak retention time or gradual merging of two peaks into one as a chromatography column declines. So that predictability and reproducibility is a real advantage when you're trying to do preparative runs or when you're doing lots of runs. And you also don't get any cross-contamination there's no adsorption on the column. So when you change from one project to another, you don't get this cross-contamination. With Prep HPLC, a lot of companies will have a Prep HPLC column for one project and another column for another project and a third column for a third project in order to avoid the danger of cross-contamination. You don't need to do that with preparative CCC. And so in total, and I've already mentioned this, it is more attractive from a regulatory point of view because the consistency, the lack of cross-contamination, the loading, all means that from a regulatory point of view, CCC has tremendous advantages when you scale it up. Now when you're talking of scale up, the two important factors are how fast you do your run and how much you can load on each run. The faster you can do your run, the more runs you can do in a day, the quicker your separation is, the more you can load, the more you get done per run. Now your speed times your load, the product of the two, is your throughput. That's how much material you process, how much pure material you create in a day or a week. Now, when you produce a graph of speed against load, here you have the speed from low to high along the axis and from low to high on the vertical axis. HPLC, preparative HPLC, sits about there. In other words, the speed is moderate, it's okay, but the loading is poor. It's a very low loading on Prep HPLC. If you go to normal phase HPLC, the speed is about the same, but the loading is slightly better. You can actually put more material onto normal phase chromatography. Flash chromatography is even better. You can see that you can load even higher amounts on. If you want to increase the speed of your HPLC, you can go for supercritical fluid chromatography, where the lower, less viscous mobile phase means you can push through higher flow rates, so you increase the speed. Now, you'll see at this point here, there's a hole in the graph about there, and that is where I want to place high speed or high performance CCC. Now here I'm talking about high loadings and high speeds, and this is for talking about the high performance machines. So the high performance machines do very fast runs and they have high loadings as well, and that's where CCC fits in for the preparative scale. So which one do we scale up? We've talked about hydrodynamic and we've talked about hydrostatic CCC. Which one do we scale up? Now, as a brief bit of revision, I'm sure you all know this by now, the hydrostatic CPC, centrifugal partition chromatography, has a whole lot of interconnected chambers and it is spun on a single axis. The mixing inside those chambers is a cascade mixing, just a sort of a jet of one liquid in through the other. On the other side is the hydrodynamic, which is spun in planetary motion and is a single coiled tube. The mixing inside the hydrodynamic is a wave mixing. The important point why it's called a hydrostatic machine is that if you are spinning a hydrostatic machine and you switch off the pump, the mobile phase pump, then your stationary phase stays where it is. It is trapped in the little chambers. So your stationary phase is held in place by the design of the machine, and that's why it's called hydrostatic. The mass transfer occurs in each of those little chambers. That says pretty much the same thing. The hydrodynamic behavior occurs in each chamber. And the most common form is the centrifugal partition chromatograph, where there is a series of interconnecting chambers and it spins on a single axis. But you need to remember that rotating seals are required. So that's a summary of the hydrostatic machine. In contrast, the hydrodynamic machine, if you're spinning a hydrodynamic machine and you switch off the pump, the flow, the phases inside will distribute themselves to each end of the coil. The heavier phase will go to the tail of the coil and the lighter phase will go to the head of the coil. So even though you're not pumping anything, if the spin stays and you stop the flow rate, the phases distribute themselves to each end of the coil, and that's why it's called hydrodynamic. So that means that the volume of stationary phase retained in a hydrodynamic machine is very dependent on the mobile phase flow rate, whereas in a hydrostatic machine it was less dependent on the flow rate. The mass transfer is via a wave mixing that occurs within each coil, in each coil loop, and the most common form is the J-type centrifuge, which we've been talking about a lot, the J-type CCC. But no rotating seals are required. You do have flying leads, but there are no rotating seals on the hydrodynamic machines. Now in this talk, I'm going to be talking about scale-up of the hydrodynamic CCC, hydrodynamic countercurrent chromatography. Although this is probably, there might be some debatable points in here, we believe at Brunel University that there are challenges with scaling up the hydrostatic machines. One of them, with a hydrostatic machine, the pressure is quite large, and when you scale it up, you can get some very high pressures. Remember, you've got rotating seals at either side, and higher pressures give you a higher challenge, a bigger challenge to keep those rotating seals with high integrity. Another challenge is the cleaning and the cross-contamination issue. If you're going to use your preparative machine for manufacturing scale runs, pilot scale runs, then you want to ensure that you're not getting any cross-contamination. And if you have hundreds of little chambers, how do you ensure that you're not getting some cross-contamination from one project to another, or one compound to another? So that's another one. It'll be harder to satisfy regulatory authorities that you've cleaned the machine properly. The removal of air on large CPC machines can be difficult. You've got all those little chambers, and trying to get all of the air out of it can be quite a challenge, and air adds another complication into your separation. And finally, it cannot cope with particulates. With all hydrostatic machines, you've got the chambers are okay, but you've got these connecting tubes, and the connecting tubes can easily block with particulates. So for those reasons, we think that the hydrodynamic machines are the ones that is going to be more interesting when it comes to the scale-up, particularly if you're scaling up to preparative, pilot and manufacturing levels. So I'm going to talk about the scale-up of hydrodynamic countercurrent chromatography. These are the machines that we have at Brunel University. This is our smallest machine, known as the Mini. You can see the specification there, and I've also got the specification in these brochures here. We don't sell the machines, I have to say. The machines are largely sold by Dynamic Extractions, but these are the machines that we have within our bioprocessing centre, and I've copied the table with the specifications in here. You're welcome to pick up these leaflets. The Mini CCC machine, this one here, has a 17 milliliter volume of coil, 0.8 millimeter bore, spins at 2,100 revs per minute. High G-force spin. There's reasons for that, which I will go into detail later in my talk, why it's a high G-force machine. But 2,100 revs per minute. Typical separation time will be about 20 minutes for a peak with a distribution ratio of 1. And typical loading on this machine will be anything from 5 to 30 to even up to 50 milligrams on a machine this size. As you can see, it's about the size of a microwave oven. Now, to be able to inject 50 milligrams on a machine this size is quite impressive. Because on a HPLC, you'd need quite a large HPLC to be able to do that. This is the middle-sized machine. The volume here is 930, so almost a litre. The coil bore, you can see, is 3.6 millimeters. Spin speed 1,400 revs per minute. You don't need to spin so fast because you have a greater radius for your spin, so you can get the same G-force with a lower rate of spin. So it's 1,400. Typical flow rate is, we would use it typically at around about 50 milliliters a minute. Same sort of runtime, 20 minutes for a distribution ratio of 1 peak. And the loading on this will be anything from 5 to 25 grams of material. So definitely a preparative machine. This is the 5-litre machine. The coil bore, you can see, is 10 millimeters. Maximum spin speed is 850 revs per minute, but we typically run it at around about 650 because we don't need to go up to 850. I'll show you why in my presentation. Flow rate range is usually around about 600 mils a minute. Still the same runtime, 20 minutes. So still the same runtime for D equals 1 peak. And we can inject anything up to around about 300, 350 grams on this machine. And the biggest machine that we've got is this one here, 18-litre machine. Same bore size, 10 millimeters, same spin speed, and we tend to spin this one at around about 500, 600 revs per minute. Flow rate is anything up to 3 litres a minute, but typically we'll use it at maybe 1 litre a minute flow rate. Same run time, notice, 20 minutes run time, and we can inject up to 1 kilogram of material per run on this particular machine. All of these machines are housed in the Bioprocessing Centre at Brunel University. Any of you are welcome to come and visit us. We're a research centre. We don't have any secrets in the machinery and what we've got in the Bioprocessing Centre. And I would suggest a good plan would be to come to the conference at Lyon in July. And London is only a short trip away, and I'll be happy to see any of you and I'll show you around the centre, show you the machine. And we can even look at seeing how you could do some separations. So this is the Bioprocessing Centre. Consists of 5 laboratories. So we've got 5 laboratories just purely researching countercurrent chromatography. And within there, this is the pilot scale laboratory, the hazards lab we call it. What you can see there is the 5-litre machine. On the right-hand side is the pumping system, and what you can't see is the 18-litre machine over the other side, that's out of the picture. In the front is a computer, a laptop with the software that runs the machines. But the important point about this particular operation here is that the computer is in a different room. It's in an operator room. You're taking the picture through a sheet of explosion-proof glass. All of the equipment in that room is remotely operated. You put protective equipment on, such as the usual lab coat and gloves and mask if necessary, in order to go into the room to set up the machines, to put your sample, to load your sample, to put the solvent systems in place and so on. But once you've done all the setting up of the machines, you then come out of that room, shut the door, and you go into the operator room, and you can then run the machines from the operator room. And here is one of my colleagues, Peter Hewitson, doing a run. So he is performing a CCC run on a large preparative machine. So it's entirely operated from the operator room. The nice thing with the operator room is it is a clean room. You can take your cup of tea in there and your sandwiches. Yeah? The software was designed specially for us. It was a modification that Armand did for us. I don't need to go through details of the software. Here are the two CCC machines. Yeah? This is a 6-head pump, which is the elution pump. 3 of the heads will pump one phase, and 3 of the heads will pump the other phase. So we get a nice smooth flow with 3 heads, but we can very quickly switch from one phase to the other. And we've got all this complicated valving system in order to be able to do that. We have another pump here in order to introduce the sample. That's, we can introduce a sample from the upper phase, from the lower phase, or from both if necessary, using this other 6-headed pump. There are 2 detectors. We've got the whole flow goes through a UV detector, but then we've also got a bleed to a light scattering detector to make sure we don't miss any components. And then we've got the fraction collector just down here, so we can collect all the fractions. So it's quite a good system with a good bit of flexibility in how we operate it. Now, let's talk a little bit about the theory of the scale-up. You've seen this diagram several times. Basically, the more stationary phase you retain in your CCC coil, the better resolution you get. So a lot of effort goes into trying to retain a high percentage of stationary phase in the coil. Now, as you know, when you increase the flow rate, you get less stationary phase in your coil. You just push more of the stationary phase out. This is a plot known as the dew plot from the person who discovered it. What you have is the percentage stationary phase retention from 0 to 100, and along the bottom is the flow rate that has been squared. It's the square of the flow rate, because then you get a linear relationship between the stationary phase retention and the flow rate. So this is a point here is at 2.2. That'll be a flow rate of 5 mils a minute. This is 10 mils a minute, 20, 40, 80 mils a minute. And you get a linear flow rate, but you get a drop of stationary phase retention as you increase the flow rate. That's as you would expect. Now, this is the line from the previous graph. However, if you increase the bore of the column, in other words, you make your column with a wider bore, this effect gets less. You get less drop in stationary phase retention with flow rate. So this one here is with a column bore of 3.73 millimeters. When you increase the bore to 5.83 millimeters, the effect is less. When you increase it to 7.73 millimeters, it's even less. So your stationary phase is more stable in the column with a greater bore, with a bigger bore. The breakthrough in understanding, and this produced a paper which I've referenced down here, was that the amount of mobile phase stays the same. But when your bore increases, that means that proportionally you have more stationary phase. And that was the breakthrough in understanding. Here's the effect it has, and I like to claim that this slide shows that scale up with CCC, it's better. It gets better the bigger you make it. Here's 4 CCC instruments. There's the MIDI with a small bore of 1.6 millimeters, a wide bore MIDI with 3.7 millimeters, and the maxi with 10 millimeters. So you've got 0.8, 1.6, 3.7, and 10 millimeters bore. So that's the bore, those are the machines down here. In the table here is the flow rate that is required to get the stationary phase retention that is up here. So if we start off in this box here, on the mini machine, on this smallest machine with a 0.8 millimeter bore, in order to get 70% stationary phase retention for this particular phase system, you will need 0.66 milliliters per minute flow rate. Now, if you say, well, I want to scale up now to 1.6 bore, and you do the calculations and say, what flow rate do I need to get the same stationary phase retention on a 1.6 millimeter bore, the calculations will tell you 1.8 mils a minute. When you do 1.8 mils a minute, when you go into the labs and actually type in 1.8 mils a minute on this machine, you don't get 70%, you get 85% stationary phase retention. So you think, okay, I can up the flow rate. How much can I up it? Well, you can up the flow rate as much as 7.2 mils a minute, and you then get your 70% stationary phase retention. Again, you can do the calculation and say, well, I now want to go onto the bigger machine, the wide bore mini of 3.7. The calculations will say 10.2 mils a minute will give you 70% stationary phase retention. In actual fact, you can have 92 mils. Yeah? And likewise, when you go up to 10 mils a minute, calculations say you will need to go 84 mils a minute. But in actual fact, you can go up to 1.3 liters a minute. So you are less likely to push your stationary phase out when you go for a bigger bore. So the machine is more stable. The bigger machines are more stable. Now, we've talked quite a bit about the G-force. I've mentioned high G-force machines. The reason is fairly obviously that, when you have a high G-force machine, you are more likely to retain your liquid stationary phase. Your machine becomes more stable. Here again, you have the stationary phase retention from 0 to 100. Here again, you have the flow rate that has been squared. So this is a dew plot. And this is one for 800 revs per minute on this particular column. And this is what happens when you spin it at 1200 revs per minute. You can see that you get an increase in stationary phase retention of about 10% for the increase in spin speed. So spin the machine faster and you can retain the liquid stationary phase better. That's as you'd expect. But when it comes to scale up, you also get higher throughput when you spin the machines faster. Here we have the sample throughput. Now this is in milliliters injected per hour. So that's the sample throughput, how much we do per day of injections or sample. And here's the flow rate. This time the flow rate is just straight in milliliters per minute. This curve here is at 800 revs per minute. This one here at 1000 revs per minute. And this one here at 1200. You can see that at 40 mils a minute, it doesn't make much difference what the spin speed is. It's about the same for all three of them. But when you come to 120 mils a minute, you have 700 milliliters injected per hour or at 800 revs per minute, or you can raise that up to 1100 milliliters per hour injected at the higher spin speed, 1200. When you come up to 160 mils a minute, then basically you start losing it all at the lower spin speed. But you're still increasing in your sample throughput, not much, it's plateaued a bit, but still increasing slightly at the higher spin speed. So you get much better throughput of sample at your higher spin speed. You might say that a higher flow rate to give you higher, in order to give you a higher throughput, might mean that you get more sample through, but you lose your resolution. Well, you do, but not by very much. This is on a wider bore column, 5.53 millimeters, and this is an injection of two standard compounds, benzyl alcohol and paracresol, I mentioned, and this is at 10 mils a minute, and you can see you get